All right, so last time we were just kind of talking about some basic aerodynamic principles. And so tonight we're just going to continue on with that. This whole chapter comes from the PAC chapter 5, which talks about aerodynamics and flight handling and stuff like that. So we're just going to kind of go through a few more topics regarding that. And we're not going to finish this week, but next week probably finish that up. So this is one of the longer sections. So the first thing is ground effects. So last week we left off and we were talking about wingtip vortices and wake turbulence avoidance. And so the next thing we're talking about here is ground effect. So ground effect is an aerodynamic characteristic of the interaction between the wing and kind of the air that gets stuck between the wing and the ground. And usually you'll notice this ground effect when you're about a quarter to a half of the wingspan away from the ground. And when you're that close, the wing becomes a lot more efficient and allows you to create more lift at a slower airspeed. And so you can take off even before what would be considered your stall speed. You can take off, like if your stall speed was 55 knots, you might be able to get off the ground at 45 knots due to ground effect and having the ability to produce this lift much more efficiently. One problem that can happen is if you're landing and you are landing too fast, you can end up in this ground effect where you just float down the runway and you can't touch down. Eventually you will touch down, but you'll probably overshoot your landing point, and that's not always a good thing. So you have to take this into consideration when you're landing and when you're taking off as well. There's actually several techniques used for what we call our performance takeoffs, which include soft field takeoffs and short field takeoffs, where you basically use ground effect to your advantage to get off the ground and get to airspeed faster so that you can perform that takeoff. After you get about one wingspan away from the ground, the ground effect stops working and basically you return to your normal aerodynamics of the aircraft. And so if you are at that stall speed, like say you're on 55 knots as your stall speed again, and you're at 45 knots in ground effect, and then you pull out of the ground effect, you're going to stall. So you have to take that into consideration and make sure that you are going fast enough. So once you get out of ground effect, you will be able to fly. And this chart here kind of just shows the curves of your thrust required and your coefficient of lift inside of ground effect. And you can see that thrust required versus velocity is a lot less in ground effect, and the total coefficient of lift in ground effect is a lot higher. Yeah, ground effect, pretty cool and useful. All right, the next big section is going to be aircraft stability. We're going to talk about stability around all the axes, and we're going to talk about what we can do to improve stability and some things that may work against us when we're talking about stability. So the first thing we have to talk about are the axes of an aircraft. So an aircraft has three main axes. It has the lateral axis, which runs between the wings, so between the wingtips, and this is how the aircraft pitches up and down. So it pitches around this lateral axis. The next axis is the longitudinal axis, and that goes between the propeller and the tail. And this is our roll axis, so this is controlled by the ailerons. And then the third is the vertical axis, and that just runs straight up and down through the aircraft. This is the yaw of the aircraft, and that's controlled by the rudder. And I think I missed this, but the lateral axis is controlled by the aileron, or not the ailerons, the elevator. So we'll use these three axes when we're talking about stability. But before we get to that, we're going to talk about what the moment is. So moment is this idea of having a force applied at some distance. So in the case of an aircraft, we have the effect of gravity and we have the effect of lift. And so these forces are acting at some distance from something else. Usually we consider the firewall our datum, and so we measure from that point, and that's our kind of our 0 point. And so we can calculate the moment arm for our different pieces of the aircraft. So backwards towards the rear of the aircraft is going to be some positive number. And so you'll have positive, what we call stations, and that's how we can calculate what the moment arm of a point is. We can use the station distance, and then we can use the weight, and we can calculate this moment number, which is important when we're talking about weight and balance. And that'll come up again, but for now, we're just going to kind of use this to kind of understand how forces are applied in the aircraft. So the further away you get from the datum, then obviously the stronger the force will be. So like a 10-pound force at the datum will not be as strong as it is, at station 70 as it depicts here. So stability, there are two main types of stability, and then there's three subtypes of each type. So the two main types we're going to talk about are static stability, or the initial tendency to move towards an equilibrium state, specifically when you change either pitch, yaw, or the bank of the aircraft. And what will happen is the aircraft is going to always want to do something after you do one of these things. So either you change the pitch, the yaw, or the bank, and it's either going to want to stay there, or it's going to want to move away from there, or it's going to want to return to wherever it was before. And that initial tendency is known as the static stability. The other type is dynamic stability, and this is how the aircraft performs over time after you change either the pitch, yaw, or the bank. And so it's not what happens initially, but after, a few seconds, 30 seconds, a minute, whatever. And what does the aircraft do after that force is applied over the long run? It might not be the same as the static stability, but it could be. So that's just something to keep in mind. And then there are three subtypes for these two types of stability. So we have positive stability, or returning to this kind of starting position. We have neutral static stability, or neutral stability. Both have it, I guess. And that is maintaining kind of the same state after it's been forced. So like this picture down here, this middle column, we can see that the ball is pushed and it just kind of stays flat. It doesn't really go anywhere else. So it kind of stays in that position after it was moved. And then the final type is going to be negative stability. So you kind of see this picture down here, the curved plane. And so you push the ball, and instead of just kind of staying in this position after it's rolled a little ways, it continues to roll down the hill, gaining speed. So these are the three types of stability, and we're going to talk about each of the axes individually and what stability looks like for each of them. So the first one we're going to talk about is longitudinal stability. So longitudinal stability is the tendency for an aircraft to move to a state of equilibrium from some sort of pitching movement. So a climb or a dive is usually what we're talking about here. So longitudinal stability, will keep the aircraft from getting into really excessive dives, or if you're climbing, it will keep you from climbing too fast and your AOA increasing too fast and you ending up in a stall. So we want to have good longitudinal stability so that we have predictable climb characteristics or predictable descent characteristics for our aircraft. The longitudinal stability is affected by three main things. So first, the location of the wing with respect to CG. So where is the wing located on the aircraft? Is it forward of CG, back of CG, right on CG, whatever that might be? The location of the horizontal tail surfaces. So your vertical stabilizer and your horizontal stabilizer play a role, more so your horizontal stabilizer, but it depends on what flight configuration I guess you're in. So so your horizontal tail where that's at. So, is it really far away from your CG? Is it really close? Is it a really short aircraft? And then finally, you have how big of surfaces are we talking about here? Are they, I don't know, 4 foot, 8 foot, whatever. 8 foot would be really big, but might be possible. So these three things determine what the stability is around this pitching axis. So having bigger tail surface, for instance, will increase stability. It allows more force to be exerted on or during a dive or during a climb, and so you can have more control. Also, if your wings are too far back of CG, your aircraft is going to have a hard time recovering from like a nose up attitude. So it's always going to want to kind of, or the other way around, it's going to have a hard time recovering in a dive because the nose is going to be, always pointed down. So these are just things to think about. And so, one way that modern manufacturers of aircraft take care of longitudinal stability is through the use of the horizontal stabilizer position. So, and not only that, but also the angle of the horizontal stabilizer. And so what they do is they will take the horizontal stabilizer and they'll put it at some angle. Usually it's not flat. And in fact, if you go and look at an aircraft, usually it's pointed down usually. And what that allows the aircraft to do is when it's flying and it's straight and level, that allows the aircraft to provide a little bit of downforce. And so usually the center of lift or wherever the wings are placed in the aircraft is slightly behind the CG. And so having this tail section provide this force kind of equalizes everything out, and it provides a lot of stability to the aircraft. So when you change flight configurations, going from straight level to a climb or something, the aircraft will, want to stay in that climb naturally, and it won't start climbing uncontrollably into a stall. And so some aircraft also, you can change the angle of the horizontal stabilizer. However, most small aircraft you are not. So it's a fixed angle, and that's calculated in the factory. So here's a chart kind of showing the types of stability again. So you have your positive static stability, and you have your neutral dynamic stability, and your negative dynamic stability. And you can kind of see what happens over time. So here on this red line, we have the negative dynamic stability. And so as this force is enacted, it over time will just get larger and larger and larger until it just grows out of control. And on the green line, we have the neutral stability. And as time goes on, nothing really changes. It stays the same. So whatever force was imparted doesn't grow and doesn't shrink, which can be useful in a lot of circumstances. And then finally, we have the orange line here, and that's our positive stability. And so as time goes on, the force kind of dampens out. And then one more image here. We can kind of see the effect of the horizontal stabilizer. So as you're flying through cruise speed, there's some downwash off of the main wings. And this downwash, along with the angle of the elevator, this downwash will hit the elevator and cause the airplane to pitch up. And so it stays in level flight, even though your center of lift is not right on your center of gravity. And then at a low airspeed, where the downwash is, there's more downwash hitting this elevator. The aircraft is going to want to naturally pitch up, even though it's it's not flying as fast. And then at a higher speed, the downwash again will kind of just half of it will kind of go under it and half will kind of go over it, and it'll help to keep the nose pointed down when you want it to be. So The elevator plays a big role in that longitudinal stability. Next, we're going to talk about lateral stability. So lateral stability is the tendency for the aircraft to return to equilibrium after a force is applied from a rolling movement. And so if you take the aircraft and you roll it and you let go of the yoke, what's going to happen? That's what we're talking about here. So normally in an aircraft, we would like the aircraft to stay in a bank. And so when you turn the airplane with the yoke and it starts to roll and you let go of the yoke, you want the aircraft to just kind of stay in the bank and not increase in bank and not decrease in bank. So there are different ways to take care of this. The one way is dihedral. So dihedral is basically the angle that we're adding to the wing to make it so that it's not flat. So this is especially prominent in larger aircraft like Boeing 737s and stuff like that. And if you look at them, their wings are not flat with the ground. In fact, they are angled up, sometimes quite a bit. And so this angling of the wings is called dihedral. And the more dihedral you have, the more stable the aircraft will be. And so the harder it will be for it to stay in a state or to get worse in a state. So it's always going to want to return to straight and level flight with the more dihedral you have. So manufacturers will put a little bit of dihedral on an aircraft to just give it a little bit of lateral stability. Another way to do to increase lateral stability is through adding sweep back to wings or just moving the wing location. So you can move the wings so that they're swept back. Like the best example would be probably some of the early fighter jets, some of the early jet engine powered aircraft. They had swept back wings. And so you can add the sweep back, which will provide more lift further back on the aircraft. And so you end up with kind of an effective what dihedral would do without adding dihedral. A keel effect. So the aircraft body itself will kind of act as a way to increase this lateral stability. And so kind of like a keel on a boat, the aircraft body as it's flying through the air will provide some stability against undesired rolling motions. And then finally, weight distribution, just making sure that, there is either even weight distribution, or if there needs to be more weight distribution on one side of the aircraft than the other, then having that ability is helpful in determining how much lateral stability you have. For instance, if you had full tank of gas on the right side and you had no gas on the left side, the aircraft is going to feel like it wants to roll to the right a lot more than it's going to want to roll to the left. And so that will play a role in how stable your aircraft is. Then the final type of stability is directional stability. So directional stability is the tendency of an aircraft to return to equilibrium after a force is applied in the yawing movement. So when you apply a force with a rudder, how likely is it to return to a straight and level flight? And so the biggest factor in this is just the fact that the aircraft is going to naturally want to weather vane. And this is the same as when an arrow is flying through the air or the weather vane on a weather station. The weather vane is going to want to point towards the wind because it has this large tail section that keeps it aligned with the current relative wind. And so the tail section of an aircraft acts in the same way. And having that vertical stabilizer and the whole body of the aircraft actually will keep the aircraft flying straight and level through the air after you make a change in the yawing movement. And so unlike rolling the airplane with ailerons, when we release the rudder pedals from making a yawing action, we generally want to return to straight flight. And so that's what happens. So when you release the rudder pedals from some action, the aircraft will straighten back out, and fly normally again. And so that's pretty handy, and it's probably one of the simpler forms of stability. All right, next we're going to be talking about forces on an aircraft during flight. So there are a lot of forces going on an aircraft, and there's especially a lot of forces when we're talking about turns and coordinated turns, and when we're talking about climbs and descents, and making sure that we're always at a constant rate of climb or descent or constant bank angle, whatever that might be. So in order to turn an aircraft, it requires more than just a rudder movement. So if you press down on the rudder pedal, the aircraft will yaw one way or the other. So it'll either yaw left or right, but the aircraft actually won't turn through the air. In order to turn, the aileron has to be banked, and banking that aircraft will cause the vertical component of lift, which was keeping you up, to slightly go to whatever direction you're making the turn in. And so we call this part of the lift component the horizontal component. And so the lift vector splits into two vectors. And so you have a horizontal component now, and you have a vertical component. And the horizontal component is going to turn the aircraft in whatever direction you're wanting it to go. And when you create this horizontal component of lift, you also create another force, which is acting in opposite to it. And that is the centrifugal force. And that's going to be pointing towards the outside of the turn, whichever direction that is. During a turn, the rudder pedals are useful, actually, and they help keep the nose and tail tracking in the same path so that all of the forces on the aircraft are balanced. And if they're not balanced in a turn and you get into a turning stall for some reason, you exceed that AOA, you can end up in a spin. And so it's important to keep the rudder pedal or keep the turn coordinated. This is especially dangerous when you're really slow, like when you're turning on final, when you're landing. And so the rudder pedal is used to keep the airplane tracking along this path through the air. During a bank, however, obviously you're losing some of that vertical component of lift. And so in order to compensate for that and to keep the airplane at the same altitude, you have to increase the angle of attack. And so as you're pulling through the turn, you usually have to pull the nose up a little bit so that your vertical component of lift is increased enough to keep the aircraft flying at the correct altitude. And if you ever do flight training, you'll perform a maneuver called a steep turn. And the whole point of this maneuver is to do exactly this, is to demonstrate your ability to put the aircraft into a steep bank and to keep the aircraft at the same altitude the whole time. There are two things that can happen if, for instance, you don't use your rudder pedals during a turn. And these are called slipping and skidding turns. So a slipping turn occurs when the aircraft is not turning at a rate that is appropriate for the bank angle. And you'll basically cause the nose to turn out towards the outside of the curve. And so this obviously is not desired. And so what you have to do is you'll have to correct that nose pointing outwards with rudder to push it back towards the correct track of the turn. The other type is a skidding turn, and this is where the aircraft moves towards the outside of the turn. So the nose is going to be pointing towards the inside of the turn. And again, you counteract this with your rudder pedals. And inside the aircraft, we have an instrument that is called a turn coordinator. I think I showed a picture of this a few weeks ago. And it looks like it has a little aircraft in it, and it will represent what your bank angle is, basically. And at the bottom, it'll have like a little fluid-filled reservoir thing with a little ball inside of it. And that ball will tell you if you're in a slipping turn or a skidding turn and what your coordination is. And you always want that ball to be right in the middle of that gauge. And that means that your aircraft is flying with your nose and your tail tracking along the same path. And if it's not, then the ball will move either left or the right, and you can counteract it by applying the rudder pedal wherever that ball goes. So if it goes to the right, then you use right rudder pedal. If it goes to the left, then you apply left rudder pedal. And you can keep the aircraft coordinated in that way. And that's really important, especially, again, once you get into performing stalls or you're in really slow flight and you're making turns. So here's a picture kind of showing the whole lift scenario when you're turning. So during level flight, obviously the lift and the weight vectors are equal and opposite. When you start to make a turn, the lift vector then splits into this vertical component and this horizontal component. Then you also get this centrifugal force, which points towards the outside of the turn. And then your weight vector, obviously you still have that weight pointed straight towards the ground, but there is another vector that's created, which is the load, the resulting load, which is created by this turn, and that's pointed perpendicular to the aircraft. And then, once you get into a steeper bank turn, obviously, then your horizontal component will extend greater, and your centrifugal force will also increase. And you can see that this total lift vector is kind of pointed out at a 45-degree angle. And then if you were to exceed this, eventually your vertical component would get smaller than your horizontal component. But yeah, so hopefully that makes sense. I think I have one more slide here. Yes. So this is kind of demonstrating a slipping and a skidding turn. So during a normal turn, you see that these forces are all balanced. So we have the vertical component and all the weight and the load vectors and lift vectors. Those are all equal. But then you have the horizontal component of lift here and the centrifugal force. And these are the two forces that you want to have balanced. So in a slipping turn, we can see that this horizontal component is greater than our centrifugal force. And so this will obviously cause the aircraft to start to slip. And we have to counteract that with the rudder pedal so that the forces, again, are balanced. And then in a skidding turn, the centrifugal force is going to be greater than the horizontal component of lift. And so we're going to move towards the outside, or our aircraft's going to move towards the outside, and those are going to move towards the inside. And so, again, we'll counteract that with our rudder pedals. Next, we're going to talk about some forces during climbs and descents. So I don't really have any text for these, but I'm just going to kind of go through them with these pictures. So during straight and level flight, like we were just talking about, you have the horizontal component, or the vertical component of lift, counteracting the weight vector. Those should be equal, and they should be the same. And that just tells us that the aircraft is not accelerating, and it's just kind of flying through the air normally. If we want to increase in altitude, we have to increase our lift vector. And so there's a few ways to do this. One is to increase the airspeed, and two is to increase our angle of attack. And so what we do is you can do both, really. So you increase your airspeed and you increase your angle of attack, and that'll cause the lift vector to increase. And so you're now producing more lift than weight, and so you're able to climb. And then once you're in established climb, your lift vector will return to normal, and then you'll be just configured for that climb attitude. And so you'll just continue to fly upwards, and you won't need that extra component of lift. The same thing happens during a descent. So in order to descend, you need to create less lift than weight. And so you can decrease your angle of attack and decrease your airspeed, and that will allow you to descend. And then this other one on the right just kind of shows the forces, all the forces on the aircraft during a climb, and the same is true for descent. They're just reversed. So you have the lift vector and the weight vector being equal at first, and then the lift vector is greater than the weight vector, so you're able to climb. And then once you're established on that climb, they'll go back to being balanced. And in this case, it doesn't look like they actually, they did increase the thrust vector. So during the climb, they increase the thrust in order to counteract that slowing of airspeed. All right, now we're going to switch gears a little bit and talk about the propeller. The propeller is kind of important, you know, it drives us through the air. And on single engine aircraft in particular, but also multi-engine aircraft that have propellers that rotate in the same direction, this can cause problems. So propellers come in two different kinds. So we have fixed pitch propellers and variable pitch propellers. Fixed pitch has some calculated pitch along the entire blade, and you can't change it. However, it's usually engineered in such a way that it is most efficient during some phase of flight. So takeoff, climb, cruise, something like that. And whatever that phase of flight is, it will produce the maximum amount of thrust for that. And whenever you're not in that flight configuration, it will produce less thrust. So that's just kind of a side effect. However, they're usually optimized for a wide range of different flight attitudes, kind of like an all-season tire in that way. In a variable pitch propeller, we're not going to really talk about these very much, but basically you can change the blade angle to compensate for whatever flight configuration you're in. So if you're going to take off, if you're in cruise, you're going to have different blade angles. And so you can change that to get the best efficiency out of your aircraft. The propeller is basically a wing. It's rotating in front of the aircraft, and so it produces a lift vector forwards, and it pulls you through the air. And so if you looked at a wings or a propeller and you kind of cross-sectioned it, it looked just like a wing, and it acts just like that. So the propeller is out front, and it's big, and it's metal, and it's spinning. And so it has a lot of forces that it can cause. And these forces will give us what we call the 4 left turning tendencies. So there are these 4 left turning tendencies are something that will come up again and again and again. So these are good things to know. Basically, the propeller spinning causes these 4 things to happen, and it causes the aircraft, at least when you have the propeller rotating from the pilot's perspective in the aircraft, the propeller will rotate to the left. So outside the aircraft, it rotates the other way, but it's turning left causes these forces. There are aircraft that have propellers that rotate to the right. However, that's pretty uncommon. So most of the time they rotate to the left. And so the 4 left turning tendencies are torque, the corkscrewing of the slipstream, gyroscopic action of the propeller, and then we're going to have what we call P factor, or asymmetric loading. And these forces are most noticeable at high RPMs and low airspeeds. So right after takeoff, when you have the throttle set all the way up against the wall, and when you're really slow still. So torque. Torque is caused by Newton's third law. So you have every action, there's an equal opposite reaction. And basically the propeller is spinning one direction, and something has to spin in the other direction in order to counteract that. It's the other force. And so the engine will rotate the opposite direction, and this will cause this torque effect. And so torque can be affected in a few different ways. It can, it depends on the size and the horsepower of the engine. So obviously the more horses you have coming out of that engine, the more torque it's going to have. And then obviously propeller size, if you have a really big propeller, it's going to affect it a lot more. And then the overall size of the aircraft, which will help in resisting this torque force. During cruise, this is not as noticeable. just because of the way the aircraft is designed for stability's sake. And so the force will be less noticeable as it is when you're really slow and you're really high RPM. Next one is the corkscrew effect. So when the propeller is moving through the air, and it's operating at a high RPM, you have this slipstream that is created, and normally during cruise, it's going to be extended out further away from the aircraft, and so it won't really hit the tail section. But during slower airspeeds, that slipstream shrinks a little bit, and it will start to hit the vertical stabilizer, and the vertical stabilizer will then be pushed out to the right, and the aircraft will yaw to the left. And so this corkscrewing effect will yaw the airplane into the left turn. And this is, again, noticeable most during slow flight when this slipstream is the right length to hit that vertical stabilizer. So the aircraft's propeller is basically just a big gyroscope. And so we have these gyroscopic actions that occur. So specifically, we're talking about here gyroscopic precession. And when you have this big spinning metal object and you apply a force to it, the force doesn't happen. It doesn't affect the spinning object until 90 degrees after the point where the force was enacted. And so this is most noticeable in tailwheel aircraft, however it happens in all propeller aircraft. When the nose of the aircraft is changing pitch during the takeoff roll, and a tailwheel aircraft especially, and it's pitching up towards that level state, it's going to be enacting a force on the top of the propeller. And since the resulting force doesn't occur until 90 degrees after that, the aircraft is going to want to yaw to the left because you're putting pressure on the top of that propeller blade. And so the aircraft yaws. And this is pretty noticeable, especially when you have a larger aircraft like the P-51 Mustang. And it has this huge propeller out in the front. And it's a tailwheel aircraft. And so when you're taking off in something like that, from what I hear, it yaws pretty hard. And so obviously the propeller has a big impact on how much of this gyroscopic action is created. Then the last one we're going to talk about here is the P factor. So P factor is this tendency for the propeller to create different amounts of force depending on whether the propeller is moving up or down. And the reason for this is kind of complicated, but basically you can think about it like the propeller on the upward stroke. It has to carve through new air, if you want to think about it like that. And the propeller on the downward stroke is moving through air that has kind of already been passed through in a way. And so it moves at a slightly higher velocity. And so you end up with the propeller moving on the downward stroke, creating a lot more force than the one on the upward stroke. And so you have this asymmetric loading, and you end up with a left turning tendency. This one's probably one of the harder ones to understand. Probably didn't do a good job explaining it, but anyway, you just kind of have to trust the science on this one, and just know that that this exists. So yeah, that's all we got for tonight. Actually, if you have any questions, I'd be happy to answer them though.
Nope, seemed pretty straightforward. What you're saying about that torque force. I don't know if you've ever played the game, but have you played DCS?
No.
It's like a combat flight simulator game on Steam.
Hmm.
But the P-47 in that game, to the part of the takeoff procedure is to trim the elevator like 8% to the left already when you go to take off.
Hmm.
Because when you roll that thing, it tries to flip the plane right over. It's pretty
Yeah.
crazy.
Yeah, it's yeah, especially yeah, that's another big airplane too. Yeah, that yeah, big torque forces. So yeah, would not be surprised.
Yeah,
All
it's
right.
it's pretty fun. But cool deal. I appreciate the class again.
Yeah, no problem.